From the studios of Way Happy and Beautiful Livermore, this is Mr. Meyer in 1.7, the final section. What do we do in this final section? We like to talk about modeling data. So what math geeks love to do, take data, somehow make a model of it, and then see what we can do with that data. So we're going to jump right in and show you an example. And you can see at the bottom of your screen there's a box. So what it is there's a 8.5 by 15 piece of cardboard that my daughter wants to fill with water so she can put fish in it. And I told her, all right, but you're going to have to, she wanted the biggest tank she could have. And I said, what do you mean by the biggest? And she said, the one that holds the most water. And I said, all right, well, then that should be easy to figure out. We will cut out these little corners. So right here on this drawing, you can see that we will cut out these corners right here, and that will give us an ability to fold it up and make a box to hold the water. And how am I going to figure out how big of a square to cut out of the corner in order to get the biggest volume? Because I don't know how big to cut it. And I only got one piece of cardboard, so I better be careful. So remember, this whole thing is 8 inches by 15 inches. Right, so this is 15, and this is 8. And so if I'm going to cut it out, I don't know how much I'm going to cut out. That length is going to be X. All right. So how do you find the volume of this shape? Well, the volume of the shape is always length times width times height. And so what are those dimensions of my box? Well, you'd almost think it was 8 times 15, but it's not, right? Because the 8 inches is going to have 2 X's cut out of it. So in fact, for part A, the volume is going to be the 8 minus 2x. That's one of the sides. And the other side, the 15, he's going to have an x cut out and an x cut out too. So he has 15 minus 2x. And then the last side is going to be how high it is, and that's actually going to be x units high. So there is the volume of the box in part A. Part B asks you to find the domain, which I think is a neat question. Because it's a logical one, it's not really that exciting to be mathematical. The question is this: it's how big is the domain? What values of x are feasible? Is 10 a good value for x? Well, look at my drawing. If I cut out 10 inches, then I would cut 20 inches out of an 8-inch piece of wood or cardboard. Impossible. So therefore, my domain can't be negative because I can't add to it. And it can't go bigger than, what, 4? Because of the fact that if we cut 4 on each side, we don't have a box anymore. So my domain would be from 0 to 4. Now, I'm not going to include 4 because 4 would just cut it right down the middle. Part C says graph the function over the domain in part B. So all right. So I'm going to get my graphing calculator out. So if Sheila would come up here, please. There she is. I'm going to shrink that just so I can read what I'm doing, and then if you need, maybe I'll put it back. So I want to graph this. So I'm going to set y equals, and I'm going to take out what I had in there, so clear. And I'm going to just type it in like it is. 8 minus 2x. Exciting to watch me type on a calculator. 15 minus 2x and x. So there's the volume for my box. And then I'm going to go to my window range, and I'm going to change the x's to go from, let's go 0 to 5. I know I said 4, but I'm going to go 0 to 5 so I can just see where it goes past it. It shouldn't go very far. The y maximums, I don't know, what do you think the volume of our box is? I mean, what the heck is 8 times 15? Is 120, so maybe I got to go up to about 120. So I will go 0, let's go negative 5 to 120 and put the tick marks every 10 units is what that means. And finally, I can graph. And there you see my beautiful graph of our volume. That graph represents our volume as you remove x. As you remove 1 inch, what happens? Okay, and after some technical difficulties, we are back. And so now to continue on with this question, the thing they want us to find is what is the maximum volume that the box can hold? Well, that means I want to go to this graph and I want to find the maximum volume up here. So how do I do that? Well, again, you have this beautiful calc feature right there. So second calc, and one of them is maximum, 4. So how do you use it? It says go to the left of the maximum. So I'm going to use the left arrows, and I'm going to travel to the left of the maximum. I know the maximum is this high point up here, so I'm going to go a little bit left of it, hit enter. It says go to the right of the maximum. So I will try to go to the right of the maximum, which is about there. Hit enter. And then it says, will you guess? I don't bother. And the calculator thinks, bam, there is the maximum. Now, what do those numbers represent? It's when x is 1 2/3, it looks like, and y is about 90.74. So x is 1 2/3, and y was 90.74, I think I said. And so what is that? What do those two numbers tell me? Well, remember, x represents how much we're cutting out of the box, and y represents the volume of the box. So therefore, I know that this is going to be in cubic inches, that is volume, and this is just in inches, that is how much we will remove, and that will tell us how much to remove from the box in order to maximize the volume so the fish can have plenty of water. Let's try another one. How do you model something where you got some info? So grain's leaking through a hole, and you can go ahead and read it, but I need to know volume of a cone. And so volume of a cone is 1/3 pi r squared h. And so we have a cone here, it's a beautiful cone. It's grain that's falling down from the top here, and it's building this cone. And I happen to know that they equal the height of the cone, as I was reading, is equal to the radius of the cone. So the height of the cone is 1 foot, so 12 inches, and the radius is 12 inches, and therefore I can now be in inches. Now, why did I pick inches and not feet? Was because I was reading that the rate of it growing was 5 cubic inches per minute, and then they're going to ask me later on in an hour. So I know that I probably want to be in inches because this thing is in inches, and I probably want to be in hours if for some reason came along. So or minutes, wouldn't matter. So now that I've found that, I want to find the volume of this cone. So it should be pretty simple. 1/3 pi, now the radius is 12, so 12 squared, times the height, which is 12, so I guess just 12 cubed. So 1/3 of pi r cubed, or 12 cubed. So I'll get Sheila back. She did a good job on that last problem. And I will do 1/3 times pi. Notice the pi would not be in the denominator because I multiplied it, so it's not in parentheses with 3 pi in the denominator, so that's good. Times 12, and I'm just going to say to the third if you don't mind, because it happens 3 times. And there it is. The actual volume of this shape is 1809.557. So a little approximate 1809.557 cubic inches of volume of grain. So that's how much grain we have. Now it says in 1 hour it will have grown. And it will have grown 5 cubic inches per minute. There's 60 in an hour. So that means it will have grown 300 cubic inches, which means my 1809.557 in 1 hour will have grown to 300 more. So what is that? 2109.557 cubic inches. So that's our new volume. So 1 hour later, our new volume is that. And now the question is, how tall will it be? So I'm going to just work backwards. I want to find the height now. So since those two are constant, then I know still that volume equals 1/3 pi, and then I guess I'll call it r cubed, but that's kind of silly. But these guys are always the same, so that's why I called it one thing. So I know that the 2109's got to be in there. So I'll add 300 here just so I have the number in my calculator. And now what do I do? That's on the left side. That's going over here for volume. So I will have to multiply that by 3 to get the 1/3 over. I will have to divide it by pi. So divide that by pi to get the pi over. And now finally, I can go ahead and cube root it. So I will raise it to, I'm going to raise it to the 1/3 power, it's just easier than finding the cube root button. And it's 12.63 inches. So R is 12.63 inches. And now I can tell people that according to our calculations, the height of the new cone will be 12.63 inches, or in 1 hour, it will have grown 0.63 inches. So depending on how much space we had for that cone, we may have to move faster, slower, do something, right? And that's how you use just pictures and drawing and thinking out a problem to your advantage. All right, let me ask you a question, and we'll come back and talk about regression. Nice work. All right, regression is just super fun. And what it is you get a bunch of data, you go out and you measure people's foot size and or whatever according to their height, and you can get a bunch of data and you can scatter plot it, and then we try to decide what model fits it best, or which of our 12 graphs would fit it best. And that's all we're kind of doing. So here's a breakdown of what you do. You make a scattered plot of the data, you determine the shape that fits it best, and then you try to figure out using your calculator which is the best one is. So remember, there are a bunch of different types. Here's what linear graphs would look like. Here's in what chapter you'll study them in: quadratics, cubics, quartics. Notice they have 2 humps. Notice a cubic has 2 humps. A quartic had 1, 2, 3 humps. So you always have one more than you thought, or the name implies. Natural logs, right? Graphing off to the right. Exponentials have 2 types. Powers look kind of like a square root. Logistics functions, sine and cosine when it bounces in between. So all of those are great things to know, and how we're going to make our calculator figure this out. So here's our calculator. So I'm going to get Sheila fired up here again. Bring her over. First thing I want to do, obviously, is I want to turn on something called diagnostics on. So all you're going to do is you're going to go ahead and hit stat, and you're going to go over to, I think, the setup editor, if I remember correctly. Oh no, I want to do diagnostics on setup editor or something else. So where is diagnostics on? Come on. Oh, I can't remember. That's so embarrassing. All right, I can't remember where diagnostics on is. So here's the worst thing. You could go to your catalog, and so I did second 0, which is catalog, and I'm going to go to the letter D. So where's the letter D on this thing? Here it is, x to the -1. And I'm going to go down. This is every function. Your catalog has everything that your calculator can do. I'm going to go ahead and hit here, enter diagnostics on. And it says done, and you don't know anything, and we'll be done. All that will do will give us an R coefficient, which is the correlation coefficient, or an R squared, which is the coefficient of determination. It's just best to know is that the closer those numbers are to 1, the better your curve fits its data. That's all it means. So here is my data. It looks like the number of diagonals for a polygon that has n sides. So a 4-sided figure has 2 diagonals, a 5-sided figure has 5 diagonals, a 6-sided figure has 9 diagonals. Nice little data. And so what you do is this. You grab your graphing calculator, and you go ahead and you hit the stat button, and you want to edit a list of numbers. So you hit number 1, edit. Now if you have stuff in it like mine, go up and hit clear, enter. Don't hit delete because you'll panic. And then you just start typing in the list all the numbers: 4, 5, 6, 7, 8, 9, 10. And on the other side, the diagonals: 2, 5, 9, 14, 20, 27, and 35. And you'll then quit out. Your data is now in your graphing calculator, and you would like to see it. So see right here, this blue line, this y equals, it has a stat plot. So I'm going to go second y equals. And the very first one plot, I'm going to hit enter. And all you're going to do is decide if you want to turn it on or off. I want to turn it on. You're going to pick what kind of graph you want. Now you might notice that that's a scatter plot right there. The one next to it connects it, and it'll do bar graphs and stuff like that. It asks you where your lists are, so I'm there. And what kind of mark you want to use for your scatter plot. Done. So now that I've turned it on, I'm going to quit out. Now that I've quit out, I want to see the graph. So I hit graph and I see nothing except for something I graphed a long time ago. Oh, that's horrible, right? So I'm going to hit y equals, I'm going to clear that graph out. And then I'm going to hit zoom, and there's a zoom number 9, I believe, is zoom statistics. And what that does is it'll fit your window to whatever your stat is. And there it is. There is my data in zoom statistics. And so now your job as the mathematician is to figure out what data that looks like. Does a line of best fit look good, or do you think a parabola would look better, or a cubic, or a power function, or what would you pick in all your different lists that you would get to choose? And so here I go. I'm going to try a line of best fit. So I hit stat and I go over to calc, and the line of best fit is right there, number 4, linear regression. It says the x's are in list 1, yep. The y's are in list 2, yep. The cool thing about the new update here is to store the regression equation where. I want to store it in y1. So I need to tell it to go to y1. So where that is, I think there's a but I can't remember, a shortcut. So I hit variables, go over to y variables, function, and hit number 1. And then I go down to calculate, and it thinks about it, gives me the equation, and then I hit graph, and look, it'll even put the line right through it. And that is the line of best fit that the calculator found for your data. Now, if I go back one more time to what it told me, I don't have it there, you'll see the r squared and the r values, 9.7, 9.8. That's a pretty good. Let's look at the r value. 9.8 is a pretty good, right? The closer you are to 1, the better, absolute value. Closer you are to 1, better. And so that's a pretty good one. So the r, I wanted r squared values, I'm sorry, is 0.976. So 0.976. And then I'll just do now a regression for cubic. So say we think a cubic model was better. So we would go second hit stat. I'm losing my mind. Hit stat, go over to calculate, and do a cubic regression, which looks like number 6. You fill in all the stuff. If you want to see the graph, you can. So I'll probably stop after this, but here I will do the graph one more time. And now if I go down to calculate, it will calculate it up. Look at our r squared is a 1. We nailed it. We're perfect. And if you check the graph, it should show you it's going to go through every single point. So a cubic is fabulous, and I guess it would be pointless to move on. But just for fun, that's our winner. I wonder if a quadratic would have been a winner too. So in fact, I should have paid attention again to what it gave me on that value, because I think, yep, a was 0. So look at our cubic would have a 0 for the x cubed term. This is just what you plug in for a, b, c, and d. And it would have just been a quadratic. So I know the quadratic's going to be better, or the same, I should say. So you go over to calc, and you could do quadratic regression number 5. And see, usually I'll just go down here to calculate, and I'll hit enter and see what it says. It's like r squared's 1, so boom. I could do the power regression. So if I wanted to see a power regression, I would go to stat, over to calculate, go down until you find power regression, which is coming. There it is, power regression. Same old stuff here. I'll put it in the graphing calculator one more time just because it's neat to see. And then I hit calculate. Look at our r squared. Yuck, it's 0.99, but that's not as bad as I thought it would be. So 0.99 is pretty good. If I check the graph, you can see it's hitting almost all the data points. That's pretty neat for a power regression. You could do quartic, you could do exponential. What kind do you think's the best? I already know quadratic's going to be my winner because it was the 1 value. So would cubic, so would quartic, but they would actually just turn into quadratics because they would have zeros for their terms. That's it. Stay happy, and I'll see you tomorrow.